Okay, thanks for viewing my talk on demand. I'm Dan Westervelt, and I'm going to be talking about the first measurements of PM 2.5 in Kinshasa, the Democratic Republic of the Congo, and Brazzaville, Republic of Congo. And so I want to acknowledge all of my excellent co-authors, including several from universities in the Republic of Congo and the Democratic Republic of Congo. And I just also want to give a shout out to some folks in my group who have contributed to a lot of this kind of work, pictured here. And in particular, I'd like to call attention to Celeste McFarlane, who is an undergraduate student in my group at Columbia Lamont Doherty Earth Observatory. She has done the vast majority of this analysis that I'm going to present today. Our funding comes from the U.S. State Department, the National Science Foundation, and also some internal Columbia University pots of money. So our motivation is that air pollution data is extremely sparse globally, as shown in this figure from a paper from Randall Martin. And it's basically non-existent in Kinshasa and Brazzaville. And these are two really, really big cities. Kinshasa has a population of about 14.3 million, Brazzaville a population of 2.4 million. These are two capital cities that are in different countries but are extremely close to each other, only about 7 kilometers apart. So there's no ambient air quality monitoring in these cities, yet they are some of the biggest cities in the world and probably have a pretty severe issue with air quality. So to address this, we have deployed and calibrated a small network of 5 low-cost air quality sensors covering both cities starting in 2018. And this is part of a larger effort that my group and others are working on in addressing the air pollution data gap in sub-Saharan Africa. So we're working in a bunch of other cities in sub-Saharan Africa listed here for the last few years, and we have about 50 different monitoring sites throughout the continent. These are just some of the pictures of some of that work in various places in both East, Central, and West Africa. So high quality air quality data comes at a cost, and the gold standard for measuring PM 2.5 is using a reference grade PM 2.5 monitor, maybe a BAM 1020 or a TOM or a Teledyne or something like that. Those can be pretty cost prohibitive in places that are limited in resources. So one option is so-called low-cost sensors. And in particular, we have had success using the Purple Air devices that measure PM 2.5 for a price of approximately $250, many orders of magnitude cheaper than having a reference monitor. And these monitors, these Purple Airs, are known to correlate pretty well against reference monitors. They are sensitive, however, to changes in temperature and relative humidity, and thus, in order to really trust and get high quality data out of these low cost sensors, you need to do a co-location and a subsequent calibration with reference monitors. And so we use a co-location that we set up in Kampala, Uganda, to develop the PM 2.5 correction factors for these Purple Air devices. And so the idea is that they are different cities, but they have similar setting, they have similar environments, similar emission profiles, similar source profiles, things that we've investigated that I don't have time to go into in much detail here. So doing that co-location in Kampala has produced a very high accuracy model for and regression for PM 2.5 from a Purple Air. So what I'm showing here is, on the left is a figure of the co-located PM 2.5 data in Kampala from September of 2019 to about March of 2020. The purple line is the raw Purple Air data, uncorrected, just straight from the instrument. The orange data is the U.S. Embassy BAM 1020 data, which is a reference monitor. This is the closest reference monitor to either Kinshasa or Brazzaville in Kampala, even though it's not all that close. This is at currently the closest one to those cities. So the purple air, you can see, overpredicts the reference PM 2.5, which is sort of the orange line, pretty substantially in some cases. So if you look in here in January, it looks like the purple air is saying that there should be 200 micrograms per meter cubed of PM 2.5, but the reference monitor is something like 140. When it's that high, maybe it doesn't really matter that much from health effects, but still we would like to, have an accurate measurement. So what we do is do a simple multiple linear regression, and the expression for the multiple linear regression that we develop from our data is given above in the box here. And we split up our data into a training set and a validation set. In the training set, we build this multiple linear regression, and then the validation set, we actually test it and see how well it works. And so the sort of turquoise line here is the corrected PM 2.5, using that simple linear regression, multiple linear regression. And you can see here now we're getting an extremely close match with the reference monitor for the PM 2.5 in Kampala. And on the right, you can see the residuals between the reference and the corrected, the raw PM 2.5 here. And you can see that they're sort of close to zero, except for a few major deviations, such as that point in January. So this is just some statistics from the regression that we did. We did it both on daily and hourly data. BAM 1020 data itself is not FEM for hourly data. It's only FEM on a 24-hour averaging basis, but nonetheless, you still might want to have higher resolution data. So we do our analysis on both, and you can see that we can improve the bias from about 12 micrograms per meter cubed high to about minus 1.8 micrograms per meter cubed low. We can also increase the R squared from about 0.88 to about 0.96. We also did some random forest regressions and found similar results there. So we deployed the 5 low-cost sensors throughout Kinshasa and Brazzaville, and you can see the locations of them here on this map. So they're kind of spread out. There's only one of them in Brazzaville and 4 of them in Kinshasa. They're sort of spread out throughout the city, including one at each U.S. embassy. And if we look at the data from just the U.S. Embassy site in Kinshasa, which is kind of our flagship site that has the longest data record, and you can see here is shown both the raw purple air data in purple and then the corrected purple air data in turquoise. So let's focus just on the corrected. So we see, annual means of PM 2.5 are very high, about 55 micrograms per meter cubed for 2018, 43 for 2019, and 35 for through July of 2020. So there does seem to be some decrease, and meteorological differences don't explain those decreases. I don't have time to go into the proof of that, but we analyzed temperature and precipitation and wind and humidity data throughout this time period and did not see any influence of meteorology on PM. We also don't know of any PM 2.5 related emissions control measures in the past 3 years. But we do know that in 2020, at least in the month of April, there was a COVID-19 related lockdown restriction. And so later we'll attribute part of this decrease to that. But the median PM 2.5 annual values are quadruple the World Health Organization's annual mean guideline. And so this is a violin plot of the 5 sites plus the regional average in black for all of the data that we have. And so If we just take the daily PM2.5, that's what's plotted here. These distributions are the daily PM2.5. And we average all that up, we get about 42 micrograms per meter cubed, which would be quadruple the World Health Organization guideline for an annual mean of 10. We see some high, median, and quartile ranges, especially at this location here, where you have a lot of data in this long tail. Most of them actually have long tails. We also looked at the data, averaging it by hour of the day throughout the time periods, and so we see a similar diurnal variability in the various sites. These lines are the different sites, and the black is the regional average. And we see, for example, a morning peak correlated with increases in traffic and also increased activity in terms of cooking and waste burning and things like that. We also see a similar peak in the evening, which corresponds to probably more local open burning. The highest values we see at both the Brazzaville Embassy and at this local university location, which show a peak of about 60 micrograms per meter cubed. We also have data for 2019 and 2020 at some of our sites, and we can take the April 2019 data and compare it to the April 2020 data, and there was a lockdown in Kinshasa for basically the entire month of April. And so you can see the 2020 here in these various plots is much lower by about 15 micrograms per meter cubed than the 2019. And so the evening peak, for example, is much flatter in 2020 than it is for 2019. The days of the week you can see down here, 2020 is all lower. So this probably is not related to meteorological changes as we saw, or as I described earlier. And it may not be sort of an interannual variability issue either. If we look at the April 2018 and April 2019, the average and maximum PM2.5 in Kinshasa actually increased. So the trend was increasing at least for past 1 year. But it decreased by about 15 micrograms per meter cubed in the mean in between April 19 and 2020. We saw this in the 1 kilometer level 2 MIAC AOD retrievals over Kinshasa as well. 2020 was quite a bit lower on AOD over the Kinshasa-Brazzaville region compared to 2019 and 2018, at least from the January through July period, which is what we show here. So the bottom right panel D, shows the difference between 2019 and 2020, and you can see that although there is some noise and some differences, around the box, which is the Kinshasa-Brazzaville area, we have largely positive differences between 2019 and 2020. So just to summarize, air pollution data is extremely sparse in Africa, although from what we can tell from initial estimates, the air quality seems to be poor. Focusing specifically in Kinshasa and Brazzaville, we deployed a 5-node low-cost sensor network, the first ever of its kind in these cities. We were able to use a simple multiple linear regression method to correct low-cost air quality data towards FEM based on some collocation in Kampala. The mean bias reduced from about 12 micrograms per meter cubed to close to 0. PM2.5 in the Kinshasa area exceeds World Health Organization guidelines by a factor of 4. The network-wide mean is somewhere around 45 micrograms per meter cubed. So this is severely impaired air quality. And the COVID-19 restrictions lowered PM2.5 by about 15 micrograms per meter cubed. So with that, I'll stop and look forward to the live session. Thank you.